Before radio telescopes, astronomers never even suspected the existence of these colossal outflows of matter. Cosmic jets traveling at almost the speed of light, from the center of galaxies right out into intergalactic space. But now astronomers have discovered jets at all scales, emerging from dense concentrations of matter, not only from galaxies, but also from stars. Here, close to the summit of an extinct volcano in Hawaii, astronomers are using the James Clerk Maxwell telescope to pick up faint radio waves from gas and dust in clouds where stars are forming.
The radio waves pass to the telescope through this membrane. The membrane protects the telescope surface from wind and dust and also direct sunlight during the daytime. The membrane, of course, is transparent to radio waves which pass through unhindered onto the mirror surface. The mirror surface is not made of glass, it is made of individual panels, each of which has an aluminium surface. The radio waves are reflected from the surface upwards to the secondary mirror. They are then reflected downwards and through the hole in the primary mirror. In operation, the secondary mirror moves to and fro through a small angle on and off source to remove the sky background. We're now below the hole in the main mirror, where the radio waves pass from the hole, off this mirror, to a further mirror, and then inside the red cylinder. Deep inside the red cylinder is a very tiny diode, only 1 millimeter in size. This tiny diode is the most sensitive detector in the world for millimeter radiation. It's cooled to a temperature of only 4 degrees above absolute zero. After detection, the electrical signal is further processed and then passed to the control computer, which is in the control room.
It's the last spectrum on the map, Ian. Okay, it's finished.
Can we have the spectrum, please, Richard?
Okay.
This is a really nice spectrum, and the prominent spike in the middle is called a spectral line. In this case, it's from the molecule carbon monoxide. This spectrum is just one of a set of spectra we've just taken at different points around a newly formed star. Here is a complete set of spectra we have just scanned across the jets from left to right and top to bottom. The spectral lines do not appear at precisely the same wavelength at different places in the map. The reason for this is that in some areas of the map, the molecules are moving towards us. This shifts the wavelength of the line to smaller values. And at other places in the map, the molecules are moving away from us, moving the spectral line to larger wavelength. Such regions are technically called bipolar outflows because they have two jets emitted in opposite directions. We can process this data further to produce a more conventional map, like this. Here we see a series of slices taken through the object. Each picture or slice shows only a range of speeds of the carbon monoxide molecules in the bipolar outflow. By combining the center image with the extreme blue and red images, we get a map of the region which clearly shows the bipolar outflow. Arrows show the direction of each jet. The red one is moving away from us, and the blue one is moving towards us.
The puzzle is, what is driving these ejected jets from the cloud, which we suppose is slowly contracting under gravity? Clearly, there must be some other forces at work. In this sub-millimeter image, from the warm dust in the region, there is a hint of a bulging disk at right angles to the jets. Maybe its spin is the key. In close-up, we see that there are actually two stars there, and further investigations show it's the one on the right that is driving the outflow.
A surprising number of stars in bipolar outflows have found to be double. Perhaps this is a clue as to what's going on.
As well as bipolar outflows, there are other jets in the universe. If we jump from star formation to the final stages of stellar evolution, we find outflows are still a major feature. Most dramatic of all are supernovae, cosmic explosions of massive stars, which leave behind a tiny dense body at the center and a rapidly expanding shell of glowing gas. One relatively nearby shell, called W50, has revealed something quite extraordinary. The radio contours map didn't at first reveal anything abnormal, a wispy outer shell with a bright source at the center. But the strange shifting lines of the visible spectrum from the central bright source were without precedent. Doppler shifted red and blue lines mixed together, as if the star was receding and approaching at the same time. One amazing hypothesis to explain these spectra was of high-speed jets wobbling, that is, precessing, so that they're sometimes approaching, sometimes receding. These jets are ejected at more than a quarter of the speed of light from a minute stellar remnant, a neutron star, or possibly a black hole, dragging material from a companion star that has somehow survived the supernova explosion. 10 years later, radio astronomers made this remarkable sequence of high-resolution maps, revealing the jets themselves as blobs of radio emission, at the start of their high-speed journey tens of light-years into space. Stellar jets like this can only be seen within the Milky Way. But well beyond our galaxy, we often see truly enormous jets emerging from the compact centers of other galaxies. However, these galactic-scale jets are also millions of times further away. So how can radio astronomers see them at all? Never mind achieve such high resolution. 100 times better than the best ground-based optical telescopes. Radio waves have wavelengths thousands of times longer than optical wavelengths. That means that even the largest radio dishes cannot match, by themselves, the optical resolution of the human eye. However, radio signals from many dishes can be brought together and compared electronically, giving much better resolution.
Because we want to analyze these signals in the computer, the first thing we do is to digitize them. We do that in this rack of electronics here. You'll see one board for each of the telescopes, 7 in all. And then what we want to do is to compare the signals from each of the pairs of telescopes spread out across England. And we do that in a special purpose computer we call a correlator down here. And you'll see 21 boards in all down here, one for each of the pairs of telescopes or baselines in the array. But what do these comparisons look like?
As the Earth turns and the radio source is tracked across the sky, the waves arriving at any pair of dishes progressively move in and out of step with each other, producing an interference pattern, the blue lines. It is these periodic variations which carry information about the detailed structure of the source. In this case, it's actually a double radio source. Here, the image is synthesized from fringe patterns like this idealized one, simulating a single pair of nearby radio dishes. During the day, the pattern subtly changes, but when they're combined together, we see the first clue of a double structure. A longer baseline gives more fringes, and hence details on a finer scale are revealed. A pair of hotspots near the middle now. With more than 2 dishes, with an array of dishes, we have many baselines at different orientations simultaneously. As the Earth turns and the different views are added together, the structure of the central double source slowly becomes more evident. Longer recordings give better pictures. Finally, after further computer processing and image enhancement, even the fine jets can be resolved. It is these jets that are responsible for the commonly observed double structure, giant radio lobes extending on opposite sides of an unseen active center. To exploit this technique, the giant Lovell telescope at Jodrell Bank was combined with other telescopes across England, some existing, some specially built, forming a powerful array called Merlin. All the signals are transmitted in real time via microwave links to Jodrell Bank.
Obviously, there will always be gaps not covered by any baselines, and ideally we'd like to move the telescopes into positions so that the baselines cover the gaps. Now, with the fixed telescopes in Merlin, we can't do this. But there are arrays which have been made sufficiently flexible so that baselines of many different orientations and lengths can be covered. Such an array, the most powerful in fact, is the Very Large Array, the VLA, in New Mexico.
The Very Large Array comprises 27 antennas. They're arranged 9 on each of 3 arms, one arm to the north, one arm to the southwest, one arm to the southeast. Along these arms, we can move these antennas on transporters up to 21 kilometers away. There are a number of fixed pads along these arms in which the antennas are placed. By putting antennas on these positions, we collect information from each antenna, multiply the signals from each antenna from all other antennas, and collect 351 pairs of information which are used to make images of the radio sky.
Goal 17.
Antennas spread way down the arms give us high resolution for fine detail, and when the antennas are close together, we are looking at a very broad scale structure for low resolution and studies of large angular areas.
But Merlin has 6 times longer baselines, and that means it can resolve a source whose diameter is 1/20th of a second of arc, and that's equivalent to this penny piece seen at a distance of 50 miles.
Here, for example, is a Merlin image of 3C273, the first jet discovered. But linked up to VLA across an 8,000 kilometer baseline, we can see even finer detail closer to the nucleus itself. The technical breakthrough that made this possible was the development of extremely accurate clocks, atomic clocks based on hydrogen masers. Now it became possible to bring the signals together simply by mail. The digital tapes are recorded at widely separated locations, but at a precisely known time. This means the VLA can extend its baseline from a remote antenna in Hawaii in the Pacific to others across the Atlantic in Europe. And Merlin antennas in England can be combined with others in global arrays, enabling distant radio sources to be mapped with incredible resolution. This technique, called very long baseline interferometry, has given radio astronomy the edge in high-resolution imaging. For example, in these images of 3C273 taken only 2 years apart, they could just detect movement of the matter down the jets, which must therefore be moving very fast, close to the speed of light.
The high velocity of the jets has a funny consequence, that the light is beamed in the forward direction, and so a jet pointing at us is not only blue shifted, but appears much, much brighter than the receding red shifted jet. So at any angle other than the plane of the sky, the oncoming jet will be much, much brighter than the receding jet, and we may only in fact see one-sided jets.
Astronomers have now observed hundreds of jets emerging from galaxies at all possible orientations. Most of them indeed appear one-sided. Is the receding jet really dimmed so much we just can't see it? What we can see is the longer jets that twist and turn and bend in bright, writhing arcs, as if blown by some galactic wind. Others may even collide and interact with each other. They may look different, but they all seem to originate in the same way. A dusty torus fueling a very bright disk of material, spiraling, or as astronomers say, accreting, onto a compact core at the nucleus of the galaxy. Often long, narrow jets stretching thousands of light years beyond the parent galaxy. Is there a theoretical model to explain these observations?
The fundamental component of that structure is a massive black hole, something like 1 million to 100 million times the mass of the Sun. Around the black hole is an accretion disk which allows matter to funnel down onto the black hole, releasing tremendous amount of energy, converting basically the gravitational potential energy into the light that we see.
Is there enough gravitational energy? To answer that, we need to know the mass of the black hole.
Measuring the actual mass of the black hole is much more difficult. The only direct way is to measure the velocity of some object or material in orbit around the black hole. Just as the velocities of the planets increase when they're closer to the Sun, the velocity of material close to the black hole orbits more quickly. So if one can observe the velocity of material orbiting around the hole, one can measure the mass of the hole. If we see that the velocities are increasing as one goes in towards the center of the galaxy, then that's strong evidence that there's a compact, massive central object, presumably a black hole.
The central part of the accretion disk is the brightest part, and it shines extremely brightly, but we think that there's an obscuring torus or donut surrounding the accretion disk. When we look face on, we can see right down into the central source, the bright continuum and the rapidly moving illuminated gas there. But if we look edge on, we don't see the central source. We see a much fainter source and perhaps just a bit of glow above and below the donut. Most of the energy is absorbed by the gas and dust in the obscuring torus and is re-radiated at longer wavelengths, say in the infrared. The last component of this picture is outflow of extremely energetic particles.
Normally, we see matter flung off from the outside of spinning disks like these wheels. So a narrow jet coming along the axis of the disk must be produced by some totally different means. Somewhat like the strands of a rope coming together, the charged particles from the disk must follow magnetic lines of force that eventually emerge along the rotation axis. That gets them started. But how do these jets remain so narrow for such enormous distances?
Well, there are several possible mechanisms. The first mechanism is that the electrons that are produced close to the black hole in this accretion torus carry with them a magnetic field. This magnetic field is found, again, in the big reservoir of the torus, and these electrons carry this magnetic field with it, and it is the magnetic field that confines the jet as it bores its way through the galaxy. Another possibility is that the external pressure exerted by the interstellar medium of the galaxy, the gas that one finds between stars, is producing that confinement. In this case, the temperature and density of the material should be enough to constrain the jet in the transverse direction. However, we see that the jets make it all the way from the nucleus of the galaxy to these incredible distances, boring their way through the interstellar medium of the galaxy.
We now come to the fourth and largest scale jets, which are longer than even the largest galaxies, yet still have enough energy to produce radio fireworks after traveling for millions of years. For example, in this image made by the Dutch Westerbork array, we see a faint curving trail of radio emission from spiraling electrons, extending perhaps 10 million light-years in the wake of a meandering galaxy.
The jets from radio galaxies and quasars can travel over vast distances. In fact, if we consider the ESO building here to be the event horizon of a black hole, the jet would travel all the way down this path. It would travel out of Germany, out of Europe, and in fact it would only begin to start dissipating its energy into a fluffy radio lobe by the time it reached the Sun, about 150 million kilometers away. Now, one of the things we can deduce about this energy transport over vast distances is that the jets themselves must be almost lossless. It's only the tiny fraction of energy which is lost as the jet proceeds, which is what enables us to observe them at all. So curiously enough, it's the very inefficient jets which are the easiest to see.
From Earth, it is rarely possible to see jets at visible wavelengths. But the Canada-France-Hawaii telescope on Mauna Kea took this optical image of 3C273. It seems odd that we only see one of the expected pair of jets, even in this nearby galaxy, which shines so brightly at radio and optical wavelengths. The Hubble Space Telescope gave us this close-up view of the jet. After additional processing, we can compare it with the radio contours map made by the VLA. The radio emission clearly comes from a much broader region than the optical emission, so the electrons producing it must travel further.
we have a problem now because we see these electrons that are responsible for the optical radiation. We know that their lifetime is only maybe 100 to a few hundred years. However, the jet themselves are thousands of years long, and so there is no way that we can produce the electrons close to the nucleus and have them emit at 10,000 or 20,000 light years away. So we must have acceleration mechanisms. We must have a way of keeping these electrons alive and producing the radiation in the place where we see the optical emission.
There are two ways this might happen. One possibility is that there are a lot of weak shock waves along the path of the jet, which manage to convert some of the bulk kinetic energy into random motions of electrons, which then emit the radio waves and the light. The second possibility is that there may be viscous friction where the jet, which is moving very fast, rubs against the external medium on the sides of it, which is of course not moving so fast.
Now, when we try and make detailed physical models of these complex interactions, we realize that as well as the particle beam, there has to be a photon beam as well. This is rather like a searchlight, but in this case the photons cover a very wide range of energies. We don't see this directly. We see this by analogy with searchlight shining out on a misty night. We see the scattering of the beam from small particles of dust that are mixed with the clouds in the galaxy. Now, we can actually use this scattering as well to tell us the power of the beam and tell us how bright the beam would be if it were pointing directly towards us. Our nearest neighbor radio galaxy is Centaurus A, which can be seen very clearly with binoculars in the southern sky. We knew from the early optical observations that there were a series of curious filaments extending up in the direction of the jet. We can see faint evidence for them here, but in fact when we go to a highly magnified image made with ESO's new technology telescope, we can see these filaments much more clearly. And it's these filaments which we can use as our detector for measuring the strength of the beam out along the jet direction.
These jets appear not only in the radio and in the optical images, but also in the X-ray. Now this is remarkable because the energies of the electrons emitting at X-ray energies are much higher than those emitting at radio energies, and the magnetic fields may be stronger as well, implying there must be some reacceleration process for the electrons. So it's very challenging to produce a model which can emit at X-rays.
Another problem to answer. Perhaps the biggest mystery of all is, what is the power source deep in the core?
Massive black holes fill this bill. They can convert energy with 10 times the efficiency of nuclear power. We believe, in fact, that almost every galaxy may have gone through a phase where a massive black hole formed at its center and gave rise to a colossal outburst of energy. By studying these jets and the radio sources, we therefore have a direct way of probing what goes on deep in the centers of galaxies. And the study of these massive black holes is undoubtedly one of the most important and challenging issues in astrophysics today.